and differentials. This is differentials. Both of these topics are the type of topics that for a few minutes you're like, what are you talking about? As I'm going through it, it's hard to follow exactly what I'm saying. And then at some point you go, oh, I totally get what's happening. You know what I mean? Like they're very breakthrough topics like that. I won't say all topics are like that. Yesterday wasn't like that. It would have been easy during my graphs of derivatives to go, oh, I totally get it. Then you go do the homework and you're like, I don't think I get it at all. Those are tough topics. I wouldn't say this is like that. This will be like, oh, I think I get it. And when you think you get it, you'll totally have it. So just stick with me through it. Try and pay attention all the way through. Local linearity, a little review. Well, okay. Local linearity is about looking out and thinking something's flat. We do this every day. You know, or I hope you know, that the earth is round. You're well aware of it. I hope you believe that the earth is round. But we don't act like it's round. We act like it's flat. You know, when we look out, things look flat because locally it looks flat. For large sections of the earth, it seems pretty flat. That is, when I throw a baseball to my son, I don't take into account the curve of the earth. You know, I just throw it straight out. You know, it's straight to me. And it's straight for long distances. It's a long way out before you notice that it curves. This is why it took him so long to figure out the earth was round, because it doesn't take into effect until a long way out. Now, I am getting distracted by this, but this is an important idea in this. If you get that, you're going to get what we're going to do later with this. Even something that's really curved will seem linear close by. How close? Well, okay. We can quibble about how close. We'll get to that. It's incorporated in there at some point. So when we refer to the slope of a curve, we are actually referring to the slope of a tangent line. In fact, if we stay close enough to the point of tangency, the tangent line is actually a good representation of the curve itself. Imagining zooming in on a smooth curve. Ooh, important word here, smooth curve. We need a smooth curve to do this. If you keep zooming in, what would the graph start to look like? So here's a crazy graph that I hope you agree is very curvy. But if you zoom in at x equals 2, and I use technology here to zoom right in at x equals value 2, and I'll highlight that on my screen. Where did I put my, right here. I'm just going to zoom right in on that part of it right there. When I zoomed in, you see, it's not so curvy anymore. You know? And then if I zoom in again, I zoom right in on this part, very flat looking. If you zoom in far enough, how far? Well, that's a good question. That is a great question. I will answer by the end. How far do you have to zoom in before it really looks like a straight line? For this reason, we say that differentiable curves, giving away an answer that comes up later, differentiable curves are locally linear. What's local? I don't know. It depends on how good an answer you want. But we'll say there is a spot when if you get close enough, you can think of it as linear and your errors won't be too much. You know, it won't be too far off. What condition must be satisfied in order for the curve to be locally linear? Well, that's sort of given away in the notes here. They mentioned it a couple times. They say smooth, and then we say differentiable, and that's the condition we're talking about. We're talking about something that's differentiable there. And when it's differentiable, we know it'll be continuous, so that's already fit in there. If you were thinking continuous, you're like, yep, got to be continuous for sure, but that's within inside there. If something's differentiable, what we really mean is it's going to be smooth when you zoom in far enough. And again, how far? As far as you need to. Just keep zooming in until it's far enough. Think about the Earth. The Earth is very curved until you zoom in far enough. We've zoomed in far enough where it looks very flat here now. All right, where's my controller? Therefore, the tangent line, I'm going to highlight that. This line is the whole lesson in the whole first part of this lesson in one sentence, or the idea of it anyways. The tangent line can be used to approximate the curve at near the point of tangency since the y values are almost the same. Take a look at this picture down here, and this is the picture I'm going to keep referencing. There is a spot, and I'm just going to highlight it. I hope we can agree right in there, where the pink line and the blue line are virtually the same, even though one's a curve and one's a straight line. So if you zoom in far enough, you're good. Okay, now we know the equation of a line can be written in point-slope form as follows, and this is why we learned about this point-slope form. Y equals mx x minus p plus q. There's point slope form of a line. To be able to find this equation of a line, all you need is the slope at the point you're talking about, the slope at this point and a point. Those two things, bang, equation of a line. That simple. We spent a month or so on it in grade 9. Yeah? That tells you how far we've come in 3 short years. Consider the tangent line of the curve f at x. So if you've got some general curve here, y equals f at x, and we've got a point a comma f at a. The point of tangency, oh yeah, okay, I just said that. A comma f at a. The point of tangency is a comma f at a. Furthermore, we know the slope of the tangent at that point is f prime at a. Now, this messes people up when you start writing weird symbols like this. But all we're saying is you choose an a value. To get the y value, sub that a value into the function. And if you want the slope, take that a value and sub it into the derivative. So this is really, it looks really complicated when you start writing f at a and all this kind of stuff. But all it is a guidelines. It's guidelines of how to get these values. How do I get them? You take your a, you sub it into the function. You want the slope? Take the a, sub it into the derivative. Yeah? Okay, so not nearly as complicated as it looks when all the symbols are on the screen there. And it's in the picture here. There's the point a comma f at a, and the slope is f prime, the derivative at that particular a. Therefore, if we stay close to a, the curve can be approximated by the following line. I'm going to write the equation underneath and then write the other part above it. This is the mistake textbooks make sometimes, is they write some random equation out here and they don't really reference it down here to really make it clear to everybody who's reading where they're getting this from. If I wanted to use the line to approximate the curve, and again, just close. Let's not get caught up on how close yet, okay? Really close. If I wanted to use the tangent line to be like the curve, I'd go y equals, the slope is f prime at a, and the point is a comma f at a, so I put that in there like that. Now give that a stare down, because the first time you see that, it blows your brain up because it's unfamiliar symbols. And when you get a full equation like that, don't try and read the whole thing and understand the whole thing. Go one piece at a time. Look at each individual value. The equation of the line is, we want the slope. That's f prime at a. Okay, I'm okay so far. And now your confidence rises. Instead of your brain panicking, your confidence rises. You're like, okay, maybe I do understand this. There's x, and then the point is a comma f at a. There it is, a f at a subbed into that equation. Yeah? So actually, this is just directions on how to get the tangent line at a particular point. How do we get a tangent line at a point? We take whatever a value you want, sub it into the derivative to get slope, and then sub it into the function to get the y value, and there's your x and y value. So really, it's just doing all of those steps in one piece. Then that's why it's so confusing. Well, this is the linearization. We call it the linearization. And I'm going to put it on the screen here. I'm going to add some things. This is an approximation of f at x. And I'll just put close to a. And I want you to get used to the word calculus, close. And when we say close, we mean close enough. And you've ran into this before. Do you remember in advanced functions, again, I keep referencing it, 2 to 2.1, 2 to 2.01, 2 to 2.001. And the people who are in advanced functions might ask you, how close do you have to get? And you say, well, close enough. And they'll be like, what are you talking about? You're like, you'll know, it'll be okay. Just get close enough and you'll get the answer. And that's sort of the same thing that's going on here. How close? Close. Yeah, you'll know, it'll be okay. Don't worry about it. We know it has to be close. So here's the linearization it's called. If f is differentiable, that's the big if here. I'm not setting up to ask a question on the test that if something is differentiable. Not like mean value theorem where I wanted to be able to ask, will mean value theorem, is it satisfied? You know, there was questions in the homework like that. That's not really what we're doing here. We're just sort of noticing, this thing better be differentiable. This thing doesn't work at all, okay? at x equals a, then the equation of the tangent line, this is just the equation of the tangent line, linearization of x it's called, equals f at a plus f prime at a times x minus a. They've reversed the 2 there. And there is a reason for that, except you don't have to. The reason is, if I want to estimate this function, start with this y value and then modify from there. That sort of makes more sense as you're thinking about it, even though it doesn't matter which way you do this. It's just a different way of thinking of it. This defines the linearization of f at a. This approximation f at x equals approximately L at x is the standard linear approximation of f at a. And the point x equals a is the center of the approximation. So we could go a little left and a little right. Let's go back to our picture. When we're doing this approximation, we could go a little left and a little right. We could go either way, as long as we're close to that a value. Now, if you sort of follow what I'm saying, you're in great shape. Because once I do an example, this all falls together. So it's not like yesterday's lesson where it's like, I sort of follow it, and then the homework blows your mind. You know, this is like, if you're sort of with me, everything's going to be fine because the example really crystallizes this nicely. Hey, here, jump right in. Example. Well, determine the linearization. And when this is done, I'm going to graph this thing and its linearization so we can look at it and go, okay, I really see what's happening here. Okay. Determine the linearization of f at x equals 1 plus x at x equals 0. So what I'm going to do is I'm going to do my work over here. Like I'm going to do my linearization over here. And then any side work I got to do, I'll go over there. I really like this move. I don't know where I picked this move up. I think it was a second-year prof who was like, okay, do your work over here and all your side stuff, get it out of the way so you don't get distracted by it. So the linearization of x is f at a plus f prime at a times x minus a. I really like that version of writing it better because you're going to, when you see it, you're going to, when you see it graphed, you'll see why this is the better version of it written this way around. Okay, so over here, my side work. A equals 0. They gave me the x value we want to talk about here. So let's establish what a is. The specific a value we're talking about. This sort of goes back to when we were first learning about derivatives. Remember we used a all the time to go, this is the specific value we're going to use in the question. Somewhere along the way, someone's going to give me a. So when you have this equation back here, you're like, oh no, what's this big mess? It's okay. They're going to give you a. You're going to know what this number is, the x value to use. Now, my linearization needs f at a. So it needs f at 0, and I'm just subbing 0 into the function, and I get the number 1. I'm also going to need f prime at 0. So I need f prime at x. Ooh, okay, f at x, let me just write over top of this. F at x equals 1 plus x to the 1/2. So f prime at x is 1/2, 1 plus x to the negative 1/2, or it's 1 over 2 root 1 plus x. So f prime at 0 is 1 over 2. I did that pretty quick. Take a look at it for a second and make sure that that's good. I don't want the derivative to get in the way here, because it's not an overwhelming derivative, but it's not an easy derivative either.
We're trying to find the linearization at 0. So
At 0. A equals 0. Yeah? So linearization of x equals f at 0 plus f prime at 0 times x minus 0. Now, the fact that this is a 0 this time makes the linearization simplify up nicely, but it doesn't, in other questions, it might be like x minus 2 or x minus 5, okay? So I found these values. The linearization of x is f at 0, which I found was 1, plus f prime at 0, which I found was 1/2, and then x minus 0 is just x. And let me say out loud what that thing means. It means the function square root of 1 plus x can be estimated by this function as long as you're close to 0. How close? Oh, we're going to talk about that in just a second. But I want you to see it now. Not handwritten by me. We're going to get Desmos to help us out. And I'm going to come back to this screen. So if you got copying to do, I'm going to come back to it in just a second. What was the two functions again? Let me take it over here. Square root of 1 plus x. So my first function is going to be y equals square root, I need down here, 1 plus x. And they said we can estimate that with, what did I come up with? Y equals 1 plus 1/2 x. And I'm going to really do some zoom in here. Not because I want to show off linearization, just because so you can see what's happening. You know, that's the important thing for me. Now, what this lesson is saying is that this curve, square root of 1 plus x, can be estimated pretty accurately by the straight line, the linear line, 1 plus 1/2 x, close to 0. Do you agree by looking at the picture? There is a pretty wide section in there where it's virtually the same, like indistinguishable as we look at it. And actually, it doesn't do too bad a little farther out either, like out to about negative 0.5 to 0.5. And that's a lot less close than you might have thought. It really comes down to how much curvature, how much concavity is going on here. For things that are less curvy, this linear approximation will do a lot better. So there could be maybe the double derivative used here to think about how good it's going to be. Okay, we'll just leave that off into AP Calculus a little bit. But there is ways to go, how good will this be? For now, we'll just go, hey, as long as it looks pretty close, I'm going to take it, you know? Question?
This is like another trick we have to find the tangent at a point.
Well, actually, no real trick to finding the tangent here. That is the tangent at that point. But what I'm saying is, close to 0, this can be used to estimate this. And you go, well, why would I care? Well, because I can't do square roots in my head very easily. And there's lots of functions out there that I can't do very easily. Even something like Euler's number, e to the x, e to the 2. I have no idea. Well, maybe I have some idea, but that's really hard to do. Whereas linearizations is always easy. You just look and go 1 plus half of the x value. That's nice to estimate square roots. And gives you a little hint to what calculators and computers might be up to when they find values. They might just be tricking you. They might not be finding the square root of 7 when you put it in there. They just might be finding the square root of 7 up to a certain number of decimal places that your screen will take, and then they're done. You see? So start to wonder how it is they're programming these things to do it. Because how would you get a computer to do square root? Computers don't know anything about square roots. You've got to tell it how to find the square root. You're like, well, it'll just know. No, it won't just know anything. You've got to have a plan of action of how to get this technology to do these things up to as many decimal places as you need. I'm setting up Newton's method lesson coming up to as many decimal places as you need. Okay, so what can we do with it? It says use your linearization to approximate the value of square root of 1.02, and we won't go much farther with this in this part of the course, going how close is close enough. Hopefully you agree that 1.02 is pretty close to 1 plus x if I use 0.02 as my magic number here, if you get what I'm saying here. So linearization at 0.02. Now that's weird. That's the only weird part of the whole lesson is why did I use 0.02 there? This is 1 plus x in there. So at 0.02, I really want f at 0.02, which is equal to square root of 1 plus 0.02. This will get the answer I want. So that's a little bit strange that I had to choose 0.02 there. But the evaluation isn't too bad. 1 plus 1/2 of 0.02, 1.01. I estimate that the square root of 1.02 is 1.01. That's my estimate for my linear approximation. Is it good? Well, let's just get a little help from a calculator here and actually find the square root of 1.02. 1.02, 1.099. $50494. Oh, yes, literally just copied it down wrong. Okay, that's good. I'll just erase these ones. It's a good thing, because it wouldn't have been that close, would it have been? But I hope you, when you look at this, you're like, 099-50494, yeah. Would you agree it's pretty close? And if you don't agree, take your answer and subtract 1.01 to see how much different it is. And your calculator even freaks out. It's like, I can't even really display this really well. It's if you scientific notation people, it's 0.0000495 different. You know, it's not pretty close. Is it close enough for building iPhones? I don't know. Certainly close enough to build a Samsung phone, though, no problem there, Well, I joke, but I don't really. It depends on what you're doing, doesn't it? If I was out there building car tires, this probably is plenty close enough. But maybe if I'm building the inside of iPhones, maybe it's not close enough. I mean, so let's leave close enough. That's why I say leave close enough on the shelf. We'll have others. We'll know our application to know what's close enough. So I'll just write here, very close. And we'll leave the argument about, is it close enough, for another day. Any questions there? Hopefully seeing in action, you're like, okay, this isn't nearly as bad as it looked. I've got a formula for finding the linearization, which is an approximation to the regular curve. The result below can actually be extended to all powers of x. There was a nice little jump here for linearization. And any linearization of 1 plus x can be easily proved, and we don't prove it here. I say easily. It's a little time consuming, but it's pretty easy. That any 1 plus x with any power, this particular one I did had power 1/2, but any of those can be just approximated with 1 plus kx. Not that hard to do, actually. Little derivative work and so on. You can prove it's always true. Now, your textbook uses 1 plus x, and I think it's a mistake to use 1 plus x in this, because then they immediately start using ones that don't have regular x's in there. They actually have 5x to the fourth and so on. So I'm just going to write over top of that a helpful version of this. Maybe you won't think it's that impressive, but 1 plus x. I literally said I was going to fix it, and then I didn't fix it. I'm going to write 1 plus whatever you're talking about to the k equals 1 plus ky. So it doesn't have to be an x in there. It can be whatever you want in there. And that'll help with a few of these questions. So knowing this result, and this comes up in the homework, although it's not particularly a test question. If I had f at x equal 1 minus x to the 1/3, that's what this is, okay? Third root is 1/3. Then my linearization of this, my approximation, would be, okay, so I'm going to make myself a little bit of room here and write down this 1 plus 1 plus y to the k equals 1 plus ky. So I've got let y equals negative x and let k equal 1/3. So the linearization here will be, okay, 1 plus 1/3 of negative x. Okay, so they gave me a shortcut for linearizations. They said that for linearizations, specifically of ones that are 1 plus x to the k, there's this shortcut. You can just do 1 plus kx. That's weird if it's not just given, if there's something other than x there. So I give you this version of it, which I think is the more powerful version of it, which is put a y there so you can say whatever's in the brackets. 1 plus whatever's in the bracket. Now, here, what's in the bracket is a negative x, so I get a negative there. And the power's of 1/3, and I get a nice linearization pretty quickly there. 1 minus 1/3 of x. I'm going to do 3 in a row. So if you're like, I don't know if I really followed that, I'm going to do it 3 times in a row. Here, f at x equals (1 minus x to the negative 1). Okay, so there's the function I had this time. Does it fit the pattern? is it 1 plus something to the something? After I write it like that. Yes, it's 1 plus something to the something. Let me write the linearization right under there. It says that if you've got some 1 plus y to the k, you can write that as 1 plus ky. So I'm going to let y equal the negative x that's inside. My y is the negative x. My k is the negative 1, the exponent on the outside. And so my linearization here is 1 minus negative x, which is 1 plus x. That'll be a nice linearization shortcut there. Put that up out of the way. Well, let's just check where you're at with this, because this is the toughest one in the pile. If we can nail this, we're in great shape. I wrote my function as 1 plus 5x fourth to the 1/2. I've got my shortcut linearization, which is 1 plus y to the k equals 1 plus ky. There's my shortcut. What would you let y equal, and what would you let k equal to make this shortcut work?
Y would equal 5x to the power 4.
Yeah, good. Let y equals 5x to the power 4. What's in there? And the k is 1/2. So I get my linearization of x is 1 plus 1/2 of 5x to the 4th. So my shortcut is 1 plus 5/2 x to the 4th.
So does the linearization equal 1 plus kx or 1 plus x to the power of k?
The linearization of the function 1 plus x to the k is 1 plus kx. That's the shortcut for the linearization. You can go through the other steps I did in the previous slide, but that's a shortcut that can be generalized and used. And incidentally, it appears in the homework, but I've never selected it as a test question. It's just an interesting little thing. You're like, well, why should I do it in the homework? Well, some of these things lead to later ideas, right? The idea is, let's understand as much as we can about it, even if it's not testable. I give that advanced functions every once in a while. I make a rule. If anyone says, I don't know, did I make this rule in your class? If anyone says, is this on the test? I immediately put it on the test. The idea being, you're trying to avoid it. That's why you're asking that. Is this on the test? You don't want to have to do it. So now I'm going to put it on the test and say, there. That's how we should approach these things if we really want to learn them. You know? Okay. Any questions there about linearization? That might not be a good representation of the kind of test questions that will be out there. But this one certainly is. This one forces you to think through the whole process and go, how am I going to use linearization to approximate a tough square root? Let's agree that approximating square root 123 is not simple. Let's just think a little bit about what it could be. What could we take square root of close to it?
What's our equation for this?
See, that's the problem with this question. They don't give you any equation here. They just give you a square root they want you to find. It's our job to come up with that equation that we want to use. But what would the equation be? If we want to evaluate the square root of 123, what's probably our equation? Oh, okay, so yeah, you're answering the question I asked first, then I drifted off to another question. He says 121 is a number that we could find the square root of. So over here, our thought bubble is going, well, I know the square root of 121 is 11, and that's close to 123. So that's probably the point I'm going to use. There's the point. X value 121. If that's the x value, what's the function? That's what Luke really wanted to know. What function are we talking about? So what function are we trying to approximate here? What operation are we trying to do? Yeah. You're one step ahead of me. I wanted to stop at square root. It's the square root function we're talking about. Yes? Now, what's our close value that we can evaluate this thing at? 121, yeah? And we're going to use a value. So we want to approximate close to 121. Why 121? Because we can do 121. We want to start with 121. So our linearization of x, and if you're not right with me, wait till you see this. Linearization of x is the f value at a certain a value plus the derivative times how far you've moved off. I'm saying that differently now to really understand what's happening. Start with some y value plus how much it changes times how far away you moved. Yeah? And we're letting a equal 121. So here's my side work. F at 121 equals root 121 equals 11. And maybe that's the first moment you go, oh, now I see why you chose a equals 121. That's the value you can do. That's where you want to approximate from, where you want to work off of. So f at x equals root x. So x to the 1/2. F prime at x equals 1/2 x to the negative 1/2. F prime at x equals 1 over 2 root x. There's my derivative, and I want to find that derivative at 121. And more good news comes up. Because I chose a clever a value of 121, that I could take the square root of. When I run into it here, I get a nice derivative, a pretty nice derivative. And so my linearization is, if you want to find the square root of 123, start off with the square root of 121, which is (11) plus 1 over 22 times x minus 121. Okay, I get it. When you're first seeing these, you're like, yeah, well, this is great, but where's the 123 in all this?
Should be close to this value.
123 is close to 121. Yeah? Is it close enough? Well, okay, we can check if you want. But I think it's pretty close. 123 and 121 are pretty close. What do I do with the 123 now? I just don't have an answer. I've got a linearization, but I don't have an approximation yet.
You could still multiply that out and add like terms.
I could simplify this. I absolutely could. There's nothing wrong with that move. My question is, what do I do with the 123?
Could you put that as x?
That's the x. That's where I want to estimate here. So L of 123 is 11 plus 1/22, 123 minus 121. And so I get 11 plus, what was that, 2 over 22. It's 11 and 1/11th, or it's 122 over 11, or it's, let's get the decimal here, 122 over 11. 122 divided by, I said it and didn't type it. 122 divided by 11. 11.09090909. There's my approximation. How good is it? Just for our reference. Let's find out how good it is. 11.090909. That's my approximation using linearization. Square root. That's not it. Square root. Oh, I pressed the same button again. Menu, 1. Exit out of that. Okay. Square root 123. Here's the actual answer. 11.0905. I have to get out to the 4th decimal place before I see any differences there. So even 2 away. You know, it wasn't that close to 121. It was 2 full numbers away. Still pretty good. You know, still pretty good approximation. That's closer to a test question. So if you have questions about that, you'll definitely want to ask them now. What questions do you have about what I did there? The function's easy to choose. You better look right at it. The a value takes a little thought, something close that you can evaluate at, but then the rest is pretty straightforward. More time there? We're halfway through. It's going to be perfect timing. I wanted to be done before your break, so this is good timing. Differentials. Here's another strange topic. It's another topic in calculus that when you first start looking at the differentials, it's like, what are you talking about? And then about halfway through, I think it is, where you go, oh, it's actually pretty simple what you're talking about. But I'll try and do that simple reference early. I'll try and nail that simple reference early. I want to talk about dy dx before I even get started. And we've learned a little bit about this symbol dy dx, because when it first came up, remember? We were doing y prime, and then every once in a while, one of the homework questions was dy by dx. And it was like, why are they trying to confuse me here with this crazy symbol? And as it turned out, there was more to that symbol than met the eye. It was a very convenient symbol. And today we're going to learn a little bit more about how convenient it is. And I want to tell you that this dy dx actually represents something pretty simple. It goes all the way back to advanced functions. This is the little tiny change in y over the little tiny change in x. That's all that was going on there. It was a slope to begin with. And this was change in y over change in x. It's not quite as simple as y2 minus y1 over x2 minus x1. But it's really close. This is basically just how much did y change divided by how much did x change. That was always true. Now, a couple little details. The implication is here, though, dy and dx are really tiny. When we did in advanced functions, it was 2 to 2.1, 2 to 2.01. The implication of dy by dx is we're talking about really small numbers. The second implication is this is the slope of the tangent line, not of the curve. And we just found out in linearization those things are pretty close. I mean, the difference between the tangent line and the curve, when you're really close, is not much. You know, they're really close in their values. They look like they're almost the same. That is, if I put a ruler on the ground outside on the earth, it really looks flat. You know, close by, the tangent line is the curve in a lot of ways. But technically speaking, dy dx is talking about the tangent line. Let me read the paragraph here. The idea behind linear approximations are sometimes discussed using the idea of differentials. So we're doing similar stuff to what we just did. We're going to talk about differentials. To gain an understanding of differentials, recall that Leibniz notation is dy by dx. Although it's tempting to think of this notation as a quotient of real numbers, we must remember that it's actually the limit of quotients. So I sort of implied that it's almost as simple as y2 minus y1 over x2 minus x1. And that's not quite true. It was the limit as x got closer to the other x value. The limit as x approaches a, or the limit as h approaches 0. So this is still a limit in there. So we're not just free to just interpret these things as two little numbers. It's a limit. The variables dx and dy seen in Leibniz notation are called differentials. So when you see these now, we've got a new name for these. That's the differential of y, and that's the differential of x. And that's what and it talks right here about it. Let y equals f at x be a differentiable function. Boy, you're going to see that in all sorts of things along the way. You know, this sort of starts with, well, you got to be able to take the derivative. You know, it's got to be differentiable. The differential d at x is an independent variable. The differential d at y is d at y equals f prime times d at x. Where does this come from? Well, we found out that these two things might be sort of separable. You might be able to tear them apart a little bit. And that's what we do here. We move the dx over to the other side. That is, look here. dy by dx is f prime. If I move the dx over and multiply it over there, I get f prime times d at x. You're like, is that allowed? Yeah, I'm telling you it is allowed. It does work like that. That little dx can be moved over to the other side. So now this is the differential of y is the derivative times the differential of x. At this point, it can all be symbols. You can be like, okay, so I get you can move that symbol over, but what does it mean? And that's what I'll get to in the rest of the lesson. Notice is if dx is not equal to 0, we can divide both sides. And so these are interchangeable. The dy equals f prime dx and the dy dx equals f prime. They're just moving around. What does it mean? Well, whoa. What does it mean? I'm going to give two explanations. The first one is like the tiny, oh, I get it explanation. And then there's this crazy technical explanation. On the tangent over here, the dy, this little pink part here, how much it changes in the y, is just take the x and multiply it by the slope. Yeah, that's what's going on. If you want to know how much the y is changing, take your dx and multiply it by the slope. Let me give you a simple example. Let's say I make $10 per hour. That's my slope, $10 per hour. And I work for 2 hours. How much money do I get? How much does my bank account change by? 2 times 10. That's really all that this is saying. The change in y is the change in x multiplied by whatever slope you're going up by. That goes way back to like grade 9 type thinking. Well, this is the technical explanation of all that, so I'll move through it pretty quickly. dy is the dependent variable. It's the change in y this way. It depends on the values x and dx. If dx is given for a specific value and x is some specific number, then we can find the value of dy, just like I did there, 2 times 10. The understanding, the meaning of the differentials geometrically, consider the diagram on the right. We've got some point, x comma f at x right there, and some other point that's moved over, delta x. So this point up here, q, is x plus delta x, and this y point is y plus delta y. Those are just using the deltas to do the same thing. So the corresponding change in y is f at x plus delta x, right there, minus f at x. That's the delta y. The slope of the tangent, PR, right there, is f prime. Thus, the directed distance from S to R, here to here, is this dy we're talking about, f prime at x times dx. Therefore, dy represents how much, this is the only, if all that's like, okay, I was with you until you said all that stuff. This is the only really important line. dy is how much the tangent has changed. Delta y was how much the curve changed. And those two things might be different. What we said is if they're close, those two things will be very close. dy and delta y will be very, very close. How much the derivative changed, how much the tangent changed and how much the curve changed will be very close to each other. I don't think we need too much of that technical explanation. I wanted to bring it out there so that you can see where these things technically come from. And I wanted to mention that dy is the change in the tangent, whereas delta y was the change in the curve. Sort of like instantaneous rate, average rate. Question?
So usually the change in dy will be linear then.
Yeah, the dy is the linear change. Agreed. This is why we do it right after linear approximation or right after linearization, is dy is how much you get when you do it on a straight line. Delta y was how much the curve actually changed. So the difference between dy and delta y is how much we miss by. What the mistake by using linearization instead of the curve. What do I got? 1, A, B, C, and 2. This is another one of those situations where when I do this the first time, you'd be like, I don't know if I get it at all. Then I'll do it a second time, you're like, oh, wait a minute. Maybe I got an idea what's happening here. And by the third and fourth one, you're like, yeah. So they're good examples that way, okay? 4 examples, and then we're done for the day, are we? Oh, my little discussion about everything that's going on in our life there, okay. Use the definition of differentials to find the differential dy and evaluate dy for the given value of x and dx. Discuss the geometric interpretations of your result. What? Blah, 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 blah. Let's find dy by dx. Let's start there. Let's get dy dx, and then I can do all this other stuff later. So, dy dx. dy by dx equals 5x to the 4th plus 37. Hopefully you're good so far. I know there's some details over there that have to do with answering the rest of this question. But are you okay with the derivative so far? So, when x equals 1, see, they gave me an x value to talk about. When x equals 1, dy by dx equals 5 times 1 to the power 4 plus 37. dy by dx equals 42. You should be completely unimpressed by now. You're like, yeah, that's like, isn't that like day 1 of derivatives? Take the derivative and sub in x equals 1. You haven't done anything yet. Okay, switch colors. Here's what's new today. Therefore, the change in y on the tangent is equal to 42 times the change in x. That's differentials, saying I can find how much the tangent slope, the tangent's going to change by going 42 times dx at that x value. Question?
So for that equation, the change in y equals the change in x times f prime. So what would f prime be?
F prime in general on this curve is 5x fourth plus 37.
But what
F
would-
prime at the specific x value they gave me was 42. We've got a slope of 42 going on here. And what that means is every time you change the x, multiply that by 42 to find your change in y on the tangent, not on the curve, because this is a linear approximation. That's why we did linearization first. Oh,
So usually f prime is just a multiple, so we can get from the change of x to the change of y.
right. So then someone says, well, what if you change the x 0.01? What if you just want to move over 0.01? So when dx equals 0.01, dy will be 42 times 0.01, so the dy will be 0.42. The dy is 42 times the d at x. It says discuss the geometric interpretation. So I got some curve. I don't really know what this curve's doing. Maybe I sort of do know what the curve's doing. You know, I sort of know the curve's sort of doing something like this, and I've got my tangent line right here. Here's the geometric interpretation. At that particular f prime at 1 was equal to 42. And what I mean by that is if I move over 0.01, I move up 4.42 on the derivative, on the tangent slope. The dy, the change in the y on the tangent is equal to 42 times the change in the x at that particular point. Got to be close here. Everything's got to be close. How close? Again, leave how close on the shelf. We'll deal with how close when we get to individual applications. Okay, on a scale of 1 to 100, if you're like a 23, we're in great shape. I'm doing 4 in a row. Yeah? I'm going to do that same explanation 4 times in a row. Let me write that in words. dy is the change in y of the tangent when we move dx. Good. Great explanation. I'm not complimenting myself. I'm telling you, this is a great sentence to look at and study. Do you have any questions there? Knowing that I'm going to do 3 more in a row now. More time? More time? This is such a better video than my old one. My old one was terrible. This is the same question. It says, use the definition of differentials to find the differential dy and evaluate dy for the given x and dx. Discuss the geometric interpretation. It's the exact same question. All that is like, what? I don't get all that. Step 1, find dy dx. Yeah, if we want dy, we better get dy dx first. So dy dx. Good with that derivative? Hopefully not one that boggles your mind. They gave me the x value here. When x equals pi, dy by dx equals 3 cos 3 pi cosine of 3 pi. Can you do it in your head? Negative 1. 1, negative 1. Yeah? Just doing the graph in my head. You don't have to. You can use your calculator to check these things, of course. Ooh, am I in radian mode? I am in radian mode. Good. So then I go, what was I doing? 3 cosine bracket 3 pi negative 3. Okay, so I've got my dy by dx at that particular value. You should be completely unimpressed by that point. You're like, that's the same derivative we've always been doing. dy by dx is negative 3. Good. Now, over to differential thinking. I can isolate the dy. I can bring the dx over. The dy is equal to negative 3 dx. At that particular moment, every time you move over an x, your y is going to change by negative 3. They gave me the dx they want me to use. If dx equals negative 0.02, the dy will be negative 3 times negative 0.02, and I get dy equals 0.06. I want to use the same words I did in the previous one. What did I say? It was a great sentence. I was so proud of it. Oh, dy is the change. Okay, I started with dy. Okay. dy is the change of y of the tangent when we move dx. Now this particular dx was negative, and it just means you're going left instead of right, that's all. I'm hoping that second time through, on a scale of 1 to 100, whatever you were the first time, you moved up a little bit and went, oh, okay, this isn't so bad now that I see it in action. I'm just isolating dy and interpreting it. Question?
So if we can find the change over y and the change over x for this, then this is another way we can find the tangent line equation.
Yes. Yes, we're a step away from finding the tangent line equation. In fact, we might be jumping ahead of some steps and going, I don't need the tangent line equation to find how much it changed. I can just go like this and just figure out the change straight from there because I have the specific x value. This incorporates y equals mx minus p plus q. It's all there. It's all laying there. It's just like a more direct way to get there, but it only works for small, tiny little values. You should keep these dx and dy small. And we'll leave the discussion again for how small is small enough. We'll leave that on the shelf for now, knowing that we'll be able to handle that. That's not the worst problem in all this. The worst problem is knowing derivatives. I mean, you're like, oh yeah, derivative 3 cos 3x. You're like, no problem. No, it was a big problem. Yeah, we spent 4 or 5 weeks getting to the point where derivatives come pretty nicely for us. So don't belittle your skills of derivatives. Especially look at this one. Blast from the past here. What kind of differentiation do I need for a question like this? Implicit differentiation, Grace says. He's got the words all ready to go. So I go through this. Those of you who are doing exam review here, I go through this, and when I'm taking the derivative with respect to x, and that was the way to think about this when you're first learning, is going, okay, I'm going to go d by dx of this side equals d by dx of that side. Reminding myself that x is the important variable here. It's the independent variable in this question. So when I run into x, its derivative is 1. That's fine. That's still the same rule when you're taking the derivative with respect to x. When you run into y, you write dy dx. Because that's the derivative we don't know. We go dy dx. Why is this right-hand side a tiny bit more difficult? What's going on the right? Product rule. So derivative of the first times the second plus derivative of the second times the first. Bring all the dy dx's to one side. And then we'll hesitate for just a second. How do I deal with this mess over here?
You can factor out the dy dx.
Factor out dy dx, good.
So 1 minus x.
1 minus x. And so now I finally get my dy dx. And I'm not done with it. I got to scroll down a little bit because I want to finish this question off. before I get differentials. I want to prove that the first part of a differential question is just the old derivative calculation. So I'm going to, I don't really have room over there. Well, maybe I do. Sub in, what did they give me? X equals 2, and Y equals Mr. Todd, they didn't give me a Y value for this question. No, Mr. Todd smiles at you knowingly, lovingly, and says, no, I guess they didn't give you the Y value. Yeah, if only I had an equation for finding Y values. Yeah, so a little bit more trouble here. I think there was enough homework questions like that where I was like, hold on, just relax. Look back, is there somewhere I can sub? So that substitution move is laying everywhere. Sorry, Grace. Whoa! I underestimated the coefficient of kinetic friction there. No, I overestimated it, didn't I? Yeah, overestimated it, I think. Little side mathematics here. When x equals 2, I get 2 plus y equals 2y. I get 2 equals y, I think. Now I can carry on. All that work to find out y was 2. Okay, dy by dx equals 2 minus 1 over 1 minus 2. I get dy by dx negative 1. You are unimpressed, maybe. Maybe your implicit differentiation was good. You're like, okay, no big deal. And that is absolutely true. The first part of doing a differential equation is find dy dx. Does anyone want to take a shot at the next line? I'm going to change colors and go over here. Then how do I get dy? Which is the change in y of the tangent line. It's as simple as isolation. You bring that dx over. So I get dy equals, I'm going to leave the negative 1 in there, even though it's really just negative dx. And so if I want dy, when dx equals 0.05, dy equals negative 1 times 0.05, dy equals negative 0.05. And dy is the change in y of the tangent when we move dx. Yeah. Again, hopefully, whatever your number was when the first question's like, and then you moved up as you went through the examples. And I got one more to go after that. Do you need more of the screen here? More time? What do you need? We're good? Well, wouldn't be complete without a word problem, would it? No, of course. Let's get a word problem going here. The radius of a circle increases from 10 meters to 10.1 meters. Use dA to estimate the increase in the circle's area A. Compare this estimate with the true change, delta A, and find the approximation error. What are you talking about? Okay, well, this dA says, okay, well, let's find dA by dr, shall we? Let's get that first. And differential questions start like that. Just get the derivative first, then you can launch your ship after that. So we need a formula for area, which is pi r squared. So dA by dr is 2 pi r. Ran into this before, right? How much does the area change? It changes by the circumference if your r's are small enough. That's something I didn't say before. I just left that out. And we're finding out now. Yeah, as long as your r is small, it's changing by the circumference. It has to be just a little bit of change. You can't suddenly add on 5 meters around the outside and say that it changed by the circumference, because that's not true. They want a dA. So I'm going to write it like this time. dA is 2 pi r dr. There's my equation for dA. That tells me how much the derivative, how much the tangent is going to change based on r and dr. So 2 tough questions here. No, 1 tough question. 1 easy question, 1 tough question here. Here, r equals, what's the radius this thing starts out at? 10. Oh, that's easy. Okay, that's easy. How about dr? How much did the radius move over? 0.1? Yeah, meters. Yeah? There, now. Sometimes real world examples help to go, when I move over, when my radius becomes 0.1 bigger. So dA is 2 pi times the radius times the 0.1. I sub those in right? 2 pi, 10. There, good. So I get 20, but then times 1. I get dA equals 2 pi. I'm going to leave that exact. I'm going to leave that exact. I could go to a decimal here, but I'm going to leave it exact. Now, that's the end of the dA question. Use dA. Good. I did that. Changing by 2 pi. Good. Compare this with the true change delta A. So if that picture way back when, and why I glossed over it, is because at the time it was like, what's this dA, what's this delta A? Let's talk about what delta A means. Delta A means actually find, don't estimate it using the derivative. Actually find the change in area. This is area at 10.1, subtract area at 10. Find out what the area was at 10.1 and the area at 10, and find out how much did it actually change. It won't be the same as what the tangent said. What do I mean by that? We're doing this linear approximation. Where's my website I want to show here? And this isn't the right curve. But we're finding this approximation using the tangent. It's going to be a little bit off. Is it very far off, is what we're trying to find out. Is the dy the same as the delta y? Is the dA the same as the delta A? So, okay, 10.1. So I got to do pi times 10.1 squared minus pi times 10 squared. I'll punch this in my calculator. 10.1 squared. (102.01 pi), and that's 100 pi. Oh, that came out kind of nice. 2.01 pi. Let's just find the approximation error. I don't know if I'm in any rush to make you find approximation errors, but approximation error is I got to divide by something. And I want to talk about what to divide by here. Let's say I had a $7 billion company. And at the end of the year, we were missing $1,000. Yeah? Say Google, for instance, at the end of the year is missing $1,000. I guarantee they're not spending any time looking for the $1,000. They don't care. $7 billion, you're missing $1,000, no big deal. Me, if I was missing $1,000, I'd be freaking out. I'd be looking everywhere for the $1,000. So when you're doing errors, it's important to go, well, how far off was it compared to the whole value? Is 0.1 a large amount to be off? Is 0.01 a large amount to be off? Well, it depends on what the whole amount was. And here the whole amount was 2 pi. So you got to divide by how big is this thing? How much do I care? What percentage difference is it? And so when you do 2.01 pi, subtract 2, 0.01 divided by 2, I get 0.005, which is 0.5% error. How's my writing? Oh my goodness, that's terrible. 0.5% error. I hope you agree that's in pretty much any situation, 0.5% error we can live with. See, the 0.01 was mysterious. Was the 0.01 a lot or a little? And we don't know. Well, compare it to what we're talking about. Are we talking about a $1 billion company or are we talking about something small? I can divide it by the, in chemistry class, you call this, see for you chemistry people, percent error. I think I got this right from the chemistry teacher, equals measured, subtract actual, divided by actual. Does that ring a bell for you science people? Yeah? Take the measured, subtract actual, but then divide it by what the actual is to see how much, what's the percent off I am here. Is being 1 mole, or sorry, 1 gram off a lot? I don't know. It depends on what you're measuring. Maybe 1 gram's a lot. Maybe 1 gram's meaningless.
But if our actual is 2.01, then wouldn't we divide by 2.01? Like, how come 2 pi is our actual?
Oh, good point.
Because that's the one we came up with.
Yeah, the actual dA was 2.01. Yes, good. I don't think it changed the answer. But I agree with you that 2.01 is the answer, is the actual. Good. Good catch there. Thank you. I think in my notes I actually do that and get 0.49% error instead of 0.5. So 0.49 there. Yeah. All right. Any questions about that? Key practice. I know I say it every day. Key practice. You practice these, you're like, okay, I got them. You don't practice them, you get on the test and you fumble around and you make a mess.